Hi everyone, my name is Mitch Barnett from Accurate Sound. Thanks for taking the time to view this presentation and hands-on demonstration of understanding the state-of-the-art of digital room correction. Having been involved in many audio forum discussions, watching online videos on digital room correction, and having reviewed over a dozen digital room correction products over the past 11 years, I've come to two conclusions. One is that there is considerable misunderstanding about digital room correction, how it works, and even what problems digital room correction are trying to solve, and just as important, understanding what is possible using the state-of-the-art of digital room correction. I hope you find the content educational and practical. This presentation assumes some basic understanding of loudspeaker measurements, room acoustics, and psychoacoustics, the latter being the science of how we hear sound. Let's get started by looking at the topics I'm going to cover. What is DRC, or digital room correction, and why do we need it? DRC is a specialization of digital signal processing, or DSP, and throughout this presentation I'm just going to say DSP, which for our purposes is the same as DRC. I think it's really important to briefly discuss how DSP revolutionized the pro audio industry. The purpose is to help people understand the power of DSP, not only what is possible, but what has already taken place. This also provides the context on how we are going to leverage the same modeling and measuring techniques that were used to revolutionize the pro audio industry and how it can be applied to digital room correction. This will allow us to design and implement the best transfer function for any given loudspeaker in any given room. I'm going to walk through a couple of hands-on examples of using DSP Designer software packages that allow us to measure the impulse response in the room, design the transfer function, simulate the result, generate the filters, and remeasure with the transfer function in place. Not only can we validate the transfer function, but I think this will illustrate how incredibly powerful state-of-the-art digital room correction is. The top 3 paragraphs come from Wikipedia definition. Digital room correction is a process in the field of acoustics where digital filters designed to improve the unfavorable effects of a room's acoustics are applied to the input of a sound reproduction system. DRC is usually referred to the construction of filters which attempt to invert the impulse response of the room and playback system, at least in part. Modern room correction systems produce substantial improvements in the time and frequency domain response of the sound reproduction system. The reason why DRC is so that we can minimize the negative effects of placing speakers in rooms, linearizing the loudspeaker's frequency response, which includes all of the upstream components right to the software application itself. The idea is that the music arriving at our ears does not have any frequency or time domain distortion introduced by the speakers or their interaction with the room. So the content that is on the digital media is accurately arriving at our ears. As we will see, the level of accuracy and precision in which we can accomplish this is one of the aspects greatly underestimated in state-of-the-art digital room correction. The basic steps for digital room correction are measurement, you can only correct what you know; target design, you have to define what you want; inversion, which is the difference target minus measurement, results in the correction, i.e. the inverse; and convolution, which is the application of the resulting filters. Before we can actually create a solution, we need to better understand and model the problem domain. We also need to better understand digital signal processing. I wanted to start out with the intro to the Scientist and Engineer's Guide to DSP from 1997, which is nearly a quarter century ago. This book is available free online and worth the read if you're interested in digital signal processing. I can highly recommend it. It is the bolded sentence I would like you to keep in mind as we go through the content. I call it DSP is everywhere. So let's see how DSP revolutionized the pro audio industry, specifically the recording, mixing, and mastering of music. Many years ago, I was a pro recording mixing engineer for 10 years. Here are a few of the mixing consoles I used to record and mix music on. In the top left-hand corner, we see what's called an effects rack. Here we see some digital delays, a harmonizer, some compressor limiters, an old school analog parametric equalizer, some more digital delays, and a nifty little product called a Roland Dimension D, which was used to produce stereo effects for guitars, for example. The issue here is that these consoles were heavy and, more to the point, expensive. So $60,000 would get you an entry-level console, all the way up to $600,000, for example, for that Neve console here on the right that was picked out of the Who's recording studio many years ago, and the price goes up considerably from there. I would recommend seeing the movie Sound City for a real insight from the transition from analog to digital in the recording industry. Here we're seeing Reaper, which is a very common digital audio workstation, and a single license for your own personal use is $60. It is mind-blowing to see some of those consoles that weighed several hundred pounds and were worth tens of thousands of dollars can now be had on your computer for $60. Let's take a look. Let's see an example of this. So here's Reaper running on my computer. It's got, in this case, an example song loaded up, which is some 32 tracks long. Let's give it a listen so that you can hear what I'm talking about. Okay, that was just a quick example. I just wanted to show that, you can have unlimited channels, you can have unlimited tracks. There is full-on automation so that you can reduce the fader and then bring the fader volume up for a particular track. Everything that you would want in a mixing console is available for $60. Quite amazing. I mentioned the effects rack, and one of the analog devices in the effects rack is a compressor limiter. The most popular one over the last half century is the Universal Audio 1176 peak limiter. I'm not going to go into detail about how it actually works, but suffice to say, if you listen to music of any kind, there's no question you've heard the sound of this device without knowing it. Aside from being used as a compressor, the limiter portion prevents overloading of the signal to the target destination, whether it's digital or analog media, including cutting vinyl records or streaming. That analog device has been completely transformed into software as DSP code. I used the 1176 peak limiter, both the hardware and software versions, and can say they're identical to my ears. It's incredible to think of, really. This specialized pro audio hardware was turned into DSP software 20 years ago. I hope folks are getting the impression that DSP modeling of analog and digital hardware is quite a mature industry. Another example is this Studer A800 24-track tape recorder. I spent many an hour recording and calibrating this monster. I would never have dreamed that the same tape saturation sound I got on the 2-inch analog tape sounds identical with the DSP software. It is really amazing to see this level of DSP transformation and maturity in a similar audio industry. It's gone from $60,000 down to $200. It's simply amazing. So how is this done? We asked this as we were going to apply the same modeling and measurement principles to digital room correction. DSP modeling, how is it done? There are two basic ways for a DSP designer to develop a processing module to mimic the sonic performance of a specific analog or digital processor. One way is called the black box approach, which is to pass a variety of static and changing signals through the device, measuring the input-output characteristics for all front panel settings, and then developing the DSP code that accurately emulates those changes. The other is to examine the circuit diagram and model the various component blocks using off-the-shelf software to generate the transfer function from input to output. That mathematical function can then be used to generate the DSP routines that emulate the device in question. Most DSP developers combine both techniques along with a lot of code refinements based on prior modeling experiences and some intensive listening sessions. It's the transfer function that we're after. It's the heart of the modeling process in the development of DSP code that mimics the frequency response to time variable signals in response to adjustments via some form of graphical user interface. In other words, the on-screen knobs and switches. Now, if a circuit diagram can be located for the device, then we can actually build the circuit using a software simulators, DSP simulators, and it's able to produce a multi-differential equation that relates output level to variations in input levels and control parameters. That mathematical expression is the basic transfer function for the device, which can then be modeled in code. For example, the JUICE C++ audio framework, which is quite mature, has all the classes necessary to develop just about any kind of DSP software one wants. Remember that 1176 peak limiter? Well, here's the circuit diagram. So we have both a hardware working analog device that can be measured along with the circuit diagram that can be modeled. And we can model that in a tool called LT Spice. Basically, Spice is the de facto standard for modeling any kind of electronic circuit. So now we know how these analog hardware devices are modeled using DSP. Let's apply what we know to model loudspeakers in rooms. We can take the same approach to modeling loudspeakers in rooms, at least from a frequency response and timing response perspective. We're not so much interested in ray tracing the dispersion of loudspeakers in rooms. We are more interested in the wavelengths when it comes to digital room correction. Note, an ideal loudspeaker is a minimum phase device. I won't be going to the math behind that. Again, I can recommend the DSP book linked earlier to help understanding of a minimum phase system. A physical loudspeaker's impulse response can also be measured, and we'll be getting into that shortly. And rooms can be modeled and measured, but it's more complicated as there are more variables at play. We'll go through each one. In the end, a transfer function can be designed to restore the ideal loudspeaker's minimum phase response to one's ears using a linear phase finite impulse response, or FIR filter. The FIR filter contains both frequency and timing corrections that work independently. How do we model the ideal loudspeaker? We want to look at its specifications. So it's generally agreed upon that 20 to 20 kilohertz is the frequency response that we're interested in. A flat frequency response, plus or minus 1 dB tolerance, as we can hear a 1 dB EQ difference, and that link points to a study that I did that shows that you can hear a 1 dB EQ difference. Loudspeakers roll off below 20 hertz, as speakers typically do not go down to DC or 0 hertz. And as I mentioned before, the ideal loudspeaker is a minimum phase system. The ideal loudspeaker has no crossover network, so there's no potential phase distortions. It has ideal directivity, which we're not really interested in this particular context, but I highly recommend Earl Getty's paper on directivity in loudspeakers. It's really well done and shows what an ideal directivity response should be. Of course, we're talking about no room, so we're talking about an anechoic response. So let's open up a FIR filter tool designer to model the ideal loudspeaker. All right, so we've got Accurate, which is a DSP digital room correction software. It does much more than that. As we can see, we can apply a whole bunch of time domain functions and frequency domain functions on waveforms. But in our case, we're just looking at simulating what an ideal loudspeaker would be, and we can do that by generating a crossover whose passband is 20 to 20 kilohertz. So here I've got a little example where actually the speaker goes down to 15 hertz. We've applied a Butterworth fourth order filter. The fourth order is for ported boxes, and a second order would be for a sealed box. And also we're talking about a minimum phase device or a minimum phase system. So let's go ahead and calculate and save that, and then let's go have a look at that. All right, so I've just opened up that filter, and we can see that its frequency response is flat from 20 to 20 kilohertz, and we've got the natural roll-off that we would expect since the loudspeaker can't produce down to 0 hertz. We can also look at its step response, and here in the bottom pane we're looking at the amplitude over time, and at time 0 we're going from 0 to full amplitude with no time delay, and then this roll-off is related to the actual roll-off of the loudspeaker. So different loudspeaker roll-offs will produce different roll-offs in the step response. We can also look at the phase response, and again, this is quite normal for what we want to see. A minimum phase device basically has flat 0 phase and then increasing phase as we get down to the roll-off, the natural roll-off of the speaker. And while I'm showing a phase wrap here, it actually just continues straight up if we were to unwrap the phase. Same applies for the group delay. As we can see here, the group delay is basically flat all the way down again to the roll-off of the speaker. So if we look at all three, we can see that this is our ideal loudspeaker. Perfectly flat frequency response, flat group delay. The step response, we know what it should look like based on a minimum phase system. And if we look at the phase response, it's also flat. So this is just the idea of how we can model the ideal loudspeaker, and what we should expect if we measure the ideal loudspeaker should look very similar to this. All right, here I've taken the response that we got out of Accurate and I have imported it into REW, again just to show what the ideal loudspeaker would look like from a frequency response perspective. Also, I wanted to show a little bit about the step response and the ideal loudspeaker timing. So here we've got a little bit of a chart that again shows that at time 0 we go from 0 amplitude to full amplitude, and then we've got the roll-off, the low frequency roll-off of the speaker. Note that the vertical spike is from 20 hertz to 20 kilohertz. This is kind of the view that we're looking at. It's band limited, but what I really wanted to point out is that if there was any timing variability, we would see this move off the axis of 0 milliseconds. So again, the ideal loudspeaker and timing response. So not only can we model the ideal loudspeaker, we can also measure the transfer function of a physical loudspeaker. There is a standard method for measuring loudspeakers that can be downloaded for free. it is definitely worth a read. Being able to predict the estimated or predicted in-room response is a huge feature of the standard. While there is a plethora of measurements for the technically interested folks on speaker design and performance, the average consumer just wants to understand how it would sound tonally in their own room. As one can see, the predicted or estimated in-room response correlates very well to the in-room measurement, a validation that the predicted in-room response based on the Klippel near-field measurements works as intended. Now, if we could only get more loudspeaker manufacturers to get their products properly tested and release this information, it would be very helpful to the consumer. So what does a good speaker measure like? Here we have the JBL M2, which is a great sounding and a good measuring loudspeaker, as the device under test being measured by a Klippel near-field scanner. The beauty about this near-field scanner is that you don't need an anechoic chamber to actually record the direct sound or the frequency response of the device. This is because the Klippel near-field scanner is also using state-of-the-art digital signal processing. It's able to window out or separate the direct sound from the room reflections. Here we have some examples of that where we can see what the direct sound is and what the room reflections are. And so when we measure the loudspeaker at all the different angles, we can window out the room reflections. Now, in the case of digital room correction, it's kind of somewhat the opposite as far as low frequency is concerned. We want to have both the loudspeaker and the room come into the measurement, and then as we move up in frequency to the mid-range and the high frequencies, we actually want to window out the room reflections. And so we're only linearizing the direct sound of the loudspeaker. I think this is a very important point that goes overlooked when talking about digital room correction systems. And since the Klippel near-field scanner can use DSP to window out reflections, so can digital room correction systems, and this is what we're going to be talking about here shortly. I wanted to point out that the JBL M2 loudspeaker also uses DSP. This is the EQ transfer function that is embedded in the electronic crossover. We're using some digital IIR, or infinite impulse response filters here, and we can see that at 20 Hertz we've got about a 6 dB boost, and that at 3 kilohertz we've got anywhere from 10 to 15 dB of boost as we go up in frequency. The reason for this is because the JBL M2 uses a constant directivity waveguide, and that waveguide needs constant directivity EQ. There's an actual transfer function for that. This is because the whole idea behind constant directivity is that as you move off axis, you're getting the same response as you would on axis. One of the key differentiators of the quality of the JBL M2 loudspeaker. Here we see the results of the JBL M2 measurements on the Klippel near-field scanner. I'm not going to get into detail about how to read these charts. Suffice to say that what we're looking for is a smooth response. Here we can see while it's relatively flat, it's certainly nowhere near as close as our ideal loudspeaker is. Looking at the step response, we can see that the tweeter arrives first and then the woofer arrives second. We also note it is not the ideal loudspeaker step response either. This is something we're going to talk about in a little bit more detail, but I just wanted to put it up so that we can see what the step response look like, because we're going to look at it again later. Here's the estimated in-room response. Pretty flat, pretty smooth, but when we actually put the speaker in the room, here's the measured in-room response of a JBL M2 in a pretty good room. If we look back at the estimated in-room response, we can see that there's a little bit of a drop at about 500 hertz. We see that as well in the measured in-room response. We also see more up and down low frequency variability, which we're going to talk about next. The one thing I wanted to show though was also the step or timing response, which is pretty much identical to the measured timing response or step response, but again, not the ideal step response that we saw in our idealized loudspeaker. Here we're comparing the ideal versus the measured loudspeaker itself and then the measured loudspeaker in a room. Not only the frequency response, but also the step response. And so we're seeing the ideal step response, the measured step response, and the in-room step response. So my point in showing this slide is that as we move further away from the ideal, we find that loudspeakers have some problems and the rooms have some problems with the loudspeaker in it. And so we're specifically going to look at initially the low frequency up and downs. What is the issue there? The issue is that at low frequencies, the room is in control. Here is an example of a loudspeaker placed in 3 locations within a 2-foot radius measured at the listening position in a typical room. The graphs show the profound effects of room resonances at frequencies up to about 300 Hz, and above that frequency, sometimes referred to as the transition or Schroeder frequency, the curves change relatively little, indicating the dominance of the loudspeaker frequency response and directivity in determining the shape of the curve. The dividing frequency is a function of room size, so moving lower as the room gets larger. So this is why bass sounds so good in concert halls. If we look at some of the notes on the side here, we see that Floyd Toole, in his investigation of many rooms over the years, has estimated that something like 80% have serious bass coloration. I would agree 100%. That is my take on measuring over 125 rooms in the past 18 months. They all show a high level of variability in the low frequency response due to room reflections, room resonances, room modes, room resonances, whatever you'd like to call it. Floyd's research also shows that bass subjectively accounts for 30% of how we judge speakers' sound quality. And Floyd goes on to say any loudspeaker can sound better after room EQ, so long as it competently addresses the bass frequencies. It's not a guarantee, but should be not too difficult for the prime listener. So let's break this down even further. There are 4 zones in small room acoustics. We are mostly interested in the normal mode zone and the diffusion zone. The exact wavelength of the frequency which matches the dimensions of the room will resonate the most. Everything else will be more and more affected by phase cancellation. You can almost think of it as a giant Coke bottle. When you blow on it and you can hear that resonant sound, that would be the same as where the room dimensions match the wavelength of the frequency. What's really cool about this is to kind of get a visualization of kind of the wavelengths. And again, this is where I wanted to make sure people understand we're really interested in, from a digital room correction perspective, we're interested in the actual wavelengths. And we'll get to this as we move forward. Here we've got the wavelengths are comparable to the dimensions of the room. Room resonances, standing waves dominate. And this frequency rate here, this transition frequency, is popularly known as the Schroeder frequency. The third region, which extends approximately 2 octaves, is a transition to the 4th zone. So this diffusion zone, there's still reflections, room reflections going on, but they're not as large. They're transitioning from waves to rays. So here we've got standing waves, and we're moving into rays by the time we get 4 times the transition frequency or Schroeder frequency. So if our room transition frequency, for example, is 150 Hertz, 4 times that is around 600 Hertz. So by 600 Hertz, The room correction system should be stopped, and we'll talk about that a little bit more as we move forward. There's some great tools that we can use to help us figure out the room modes. For example, this AMROC calculator is very popular, and you can just type in your length, width, and height of your room, and out will come the room modes. Of course, there is some effect, obviously, with the construction, how the room was constructed. Is it wood or is it concrete construction? And of course, the fixtures that are on the walls of the room, how damped the room is or how bright the room is. But generally speaking, room modes are based on the actual room dimensions. I also put a little chart over here just so that people can kind of grasp what we're talking about when it comes to wavelength. For example, a 20 hertz wavelength is roughly about 56 feet. And even at 500 hertz, between 5 and 600, we're talking about 2 feet. What's really cool about this calculator is that you can take your mouse cursor and hover over any one of these room modes, and if you have your browser hooked up to your stereo system, it will output the sound at that frequency in your room, and you can get a really good idea of how your room resonates. It's also cool just to leave it on the room mode and then walk around the room, and you can hear spots in the room where it's really loud, quite a bit louder, and other spots you can almost hear no sound at all. And if things weren't complicated enough, depending on where you place your speakers near walls will have an effect on both frequency response and level. Here we see it, what is called a speaker boundary interference response, or SBIR. There are SBIR calculators for that as well that allows you to plug in your own dimensions. What we're really seeing here is that based on the wavelength and where your listening position is, we can get a reflected sound that is the inverse of the direct sound, and therefore at that point, for that wavelength or frequency, there's virtually no output or room null, and we can kind of see the various effects here depending upon what boundary, if it's a single boundary or perpendicular boundaries, or all three dimensions are kind of the same. Further yet, we can use a tool like REW Room Simulator, which allows you to place speakers, the sub, your listening position in the dimensions of your room, in addition to the elevation view. And there's several more parameters that can be adjusted, and gives you the idea of the room modes and the frequency response and the modal distribution of the room. It's great, but the reality is, in the end, that regardless of where you put your speakers in the room and where you sit, almost invariably you're going to get huge variation in the low frequency response due to room resonances. In this case, we're looking at plus 20 dB of peak-to-peak sound pressure level variation. That means that, in this case, if we're looking at 30 hertz, is down almost 20 dB compared to 40 hertz. Depending on the notes that being played on the system, there will be a few bass notes that sound really loud in the room, and then there'll be a few bass notes that sound very quiet in the room. And this is one of the prime reasons why we want to use digital room correction, is we want to even that out as much as possible, so we don't have that one note sound where it just simply is the resonant frequency of the room. Also, we want to look at in making sure that both the left and right channels are matched up as evenly as possible. This is why we get a phantom stereo image that moves based on frequency. It's no longer in the center. It may move from one side to another side as the frequency changes based on the amplitude in the room. We're talking about minimum phase systems, and let's talk about minimum phase in room acoustics. So minimum phase systems can be inverted. That's what we're talking about, which means that a filter can be designed so that if applied to the system, it would produce a flat response and correct the phase response at the same time. That's what makes for a minimum phase system. However, as it turns out, Most rooms have low frequency regions that are not minimum phase. A simple example of something that renders a response non-minimum phase are reflections that are as large or larger than the direct signal or the direct sound. Another example are actual modes in rooms, and we'll see an example of this later. I highly recommend checking out John Mulcahy's, author of RAW, his topic on minimum phase. It's really well done. Here is an example of non-minimum phase behavior. This is a great example. So this is a digital triamp system. We can see the tweeters arriving first, woofers arriving second, and the subs arriving a little bit later. But we notice that one of the subs in the room causes what would be deemed a maximum phase peak, obviously not a minimum phase response, some 30 milliseconds after the direct sound. And so that is unfortunately a specular reflection that is quite audible and usually is heard as fuzzy bass or blurred bass, or the bass doesn't sound clear. And so this is one of the causes of that. In case you have not seen this before, I would like to introduce you to James Johnston's Acoustic and Psychoacoustic Issues in Room Correction. I highly recommend downloading the PowerPoint presentation. It is the first 31 slides that we want to focus in on. I also listed a few AES papers, plus JJ's open access papers. While we are focused on this topic, other topics on why we hear what we hear are all worthwhile reads if you want to dig deeper. This slide is from JJ's presentation. It is conceptually the impulse response in a room. Imagine speakers in a room and you are at the listening position. The first sound to arrive at your ears is the direct sound or the direct signal. Then some early reflections under the 10 millisecond mark arrive, and then we also see an unfortunate late large reflection, which we saw a great example of a couple of slides back. Then there is the broadband decay of the room, and also known as the diffuse tail. In JJ's presentation, questions are raised on what do we hear and how do we equalize the sound. I have summarized this in the next couple of slides. In a room, high frequencies decay faster than low frequencies. For loudspeakers in rooms, the directivity at low frequencies is omnidirectional and narrows as the frequency goes up. The combination of those two is when we measure an in-room response, we get a tilted response with more energy at the low end than at the top end. The frequency response of the direct sound will be different than the measured response of the direct sound plus the room reflections. When it comes to room nulls, adding more energy into a null will do nothing but make it sound worse. Our ears are more sensitive to peaks than narrow band dips in frequency response, and our ears follow the spectral envelope. The conclusion on room correction from JJ's slide presentation is that at low frequencies, we want to correct the overall room response. At high frequencies, we only want to correct the first arrival timbre. Always, obviously, we should correct the gain and delay between channels. The relative correction between channels does more perceptually than the same amount of CPU applied to flattening the system analytically. Too much correction is bad. We don't want to correct for room nulls. And long window corrections at high frequencies cause the dentist drill experience because the system will be equalized to provide way too much correction at high frequencies for the first arrival signal. So let's look at a subjective and objective review of some room correction products that Sean Olive did some time ago. I've pulled one of his slides out, and here we see the most preferred room correction to the least preferred room correction, and the measured in-room response of all of those corrections, including the unequalized loudspeaker. It's very interesting to note that it is, again, a tilted response because there's more low energy in the room than there is high energy. But as you can see, it's nice and smooth and flat, and that is the most preferred. That's what we're looking for. One thing to take into consideration from a perceptual perspective is that if you look at this slide again, we're seeing the average response at the primary listening position. And again, the top response, or the most preferred, is the one that has tilted and smooth and flat, if you will. However, from our ear's perspective, that tilted response actually sounds balanced or perceived as flat. And so this is where a lot of mistakes are made in other room correction products, where they try and make the sound flat at the listening position, or the flat in-room response is definitely not the preferred target. As we've already discussed, the sound will be simply too bright. To make things even more complicated, our perception of frequency response varies with sound pressure level. So at low listening volumes, the mid-range frequencies sound more prominent, while the low and high range seems comparatively quieter. At high listening volumes, the lows and highs sound more prominent, while the mid-range seems comparatively softer. So at around 83 dB SPL, sound pressure level, C weighting, our ears hear the flattest. So this is why it's referred to as the reference level for critical listening, and also why that sound pressure level, 77 to 83 dB SPL, depending on how much compression is involved, is used to mix and master this music to balance the bass with mids, highs, and treble. This is something to keep in mind. I always use a loudness control when I listen at lower levels than 83 dB SPL, so that the bass sounds nice and full when I'm listening. Another thing to consider is the Haas effect. And I'm not going to get into this in a great level of detail, but it's worth checking out the presentation and listening on YouTube for the Haas effect. This is where a digital delay is introduced into a mono signal, and the signal split between our ears from stereo. And you most definitely can hear a 3 millisecond delay or a 10 millisecond delay when you give it a listen. It takes a little bit of training, but once you hear it, you can't unhear it. And again, this is more to do with room reflections and what it does to blur the sound, especially when we're talking at low frequencies. Now that we have a good picture of the important parameters, we can start to model and design a solution to restore the ideal loudspeaker's minimum phase response to our ears. Much like SPICE for electronics, we require a FIR filter designer that allows us to model these acoustic and psychoacoustic parameters with a high degree of accuracy and precision. Currently, there are only a handful of DSP, DRC filter designer software products in the market that can meet all of these modeling requirements. So the steps for DSP loudspeaker and room correction: we need to measure the loudspeakers, whether it's a single or multiple impulse response measurements, and I'm going to talk about single versus multiple measurements a little bit further in the presentation. Then we need to filter the measurement, typically using a psychoacoustic filter and frequency-dependent window. We also need to separate the minimum phase response from the excess phase response. We need to draw a target frequency response and apply either a partial or full range correction. We need to invert the minimum phase response, and as we talked about minimum phase systems earlier with John's paper. And then we need to determine how much excess phase correction is required, again using a frequency-dependent window and options for partial or full range correction. We can generate the linear phase FIR filters and package them up for popular music players or convolvers. We'll install the filters, give it a listen, and compare and determine the preference. I just want to point out that the acoustic measurements of the filters are being designed with this software are within a quarter of a decibel of the simulations. So the measured versus the simulation are pretty much identical. We want to talk a little bit about some FIR filter basics first. So a FIR filter with 65,536 taps at 48 kilohertz has a frequency resolution of 0.732 hertz. That frequency range spans from 0 hertz to 24 kilohertz, and if we think of a FIR filter as a graphic equalizer, we actually get 32,768 sliders for our fur equalizer. That's a lot of resolution. Infinite impulse response, or IIR filters, are minimum phase filters. They cannot adjust the excess phase, as an excess phase correction requires a time delay. So the correction of excess phase is the time-reversed excess phase. We'll get into this a little bit of detail, but this introduces a delay which cannot be achieved by IIR filters. Linear phase filters delay the input signal but don't distort its phase. So the total correction is the convolution of the minimum phase correction and the excess phase correction. The next topic we're going to get into is the psychoacoustic filtering. Remember JJ's slides from a couple slides back? So the measurement is in red. This is a high resolution impulse response measurement of the room, and we're seeing its transfer function as frequency response. So when we apply a psychoacoustic filter, we need to remember what JJ said. We don't want to correct for all of the room nulls or any of the narrow band dips, and we also don't want to correct for all of the narrow band dips in the mid-range and the high frequencies as well. So what we're talking about here is, again, the envelope response of the impulse response or the measured frequency response in the room. This is really important to remember. The next concept we're going to talk about is frequency-dependent windowing. Frequency-dependent windowing is a powerful tool for reducing the effects of room reverberations on a measured impulse response. The frequency-dependent window examines the impulse response according to its frequency components, and at every frequency it accepts a window of time that is specified as the number of cycles at that frequency and ignores any portion of the signal at that frequency that occurs outside the time window, thereby ignoring much of the influence of reverberations and reflections that arrive later than the direct sound. In state-of-the-art DSP fur filter design tools, one can specify different FDW lengths of time windows for both low and high frequencies. The values for the time window between the low and high frequencies are adjusted smoothly. Remember that the window is specified in cycles, not time. Here we see an example of frequency-dependent windowing. The red pulse is actually the impulse response of the room, and then we've got three different windows that are being applied, or a frequency-dependent window. So a 20 Hz signal has a time period of 50 milliseconds. So 50 milliseconds times 15 cycles is 750 milliseconds. At 20 Hz, the window is open for 750 milliseconds at that frequency. As we move up in frequency, we can see that at 100 Hz, it's a much shorter window. 100 Hz time period is 10 milliseconds, so 10 milliseconds times 15 cycles, is 150 milliseconds. So at 100 Hz, the window is open for 150 milliseconds. At 1 kilohertz, we can already see intuitively that it is a much shorter window. A 1 kilohertz time period is 1 millisecond times 15 is 15 milliseconds. So I hope people can understand that as you see the frequency goes up, the window gets smaller, and we're measuring the direct sound of the loudspeaker and very few room reflections. This is a key aspect to understand when it comes to frequency-dependent windowing, and of course in combination with the psychoacoustic filtering that we talked about earlier. While this example uses 15 cycles as a single frequency-dependent window setting, the DSP software we use can adjust both the high and low frequency time windows independently. This allows us to calculate the optimum frequency-dependent window sizes based on your room size and statistical analysis of modal distribution and early reflections density. This analysis gives us the smoothest integration between room plus loudspeaker below your room's transition frequency and the loudspeaker's direct sound above your room's transition frequency or diffusion zone, as we discussed earlier. Here's another way to visualize the frequency-dependent window. So on the vertical scale, we've got time in milliseconds. On the horizontal scale, we've got frequency response in kilohertz. So down at 20 hertz, we're getting close to a 500 millisecond window that's open. And then as we move up in frequency, like at 600 hertz, we've got a 10 or a 20 millisecond window. And then of course, by the time we get to 10 kilohertz, we've got only a 1 or 2 millisecond window. So to further bring this home, but I don't want to belabor the point, but it's really important to understand that at low frequencies, we're letting the loudspeaker frequency response and the room response into the microphone. And then as frequency goes up, we got less and less of the room reflections coming into the microphone. And so this is the example that we're going to go through. So now using a 6/1 cycles window, so 6 cycles at low frequencies and 1 cycle at high frequencies, we're going to solve for a particular frequency like 600 hertz. And the reason I chose 600 hertz is that that's typically where most rooms are 4 times the Schroeder or transition frequency. So again, if we remember some slides ago where the transition frequency was about 150 hertz, and so 4 times that through the diffusion zone is roughly 600 hertz. And so by 600 hertz, we don't want to be correcting very much of the room. We only want to be looking at the direct sound from the loudspeaker. If we do the math, a window width of 600 hertz turns out to be about 2.18 cycles. So 600 hertz has a time period of 1.6 milliseconds. So at 600 hertz with a 2.18 cycle window, we're getting basically a window that's open for 3.5 milliseconds at 600 hertz. That's basically the direct sound of the loudspeaker. And as we move up in frequency, the window gets even less. So therefore, at 600 hertz, anything outside a 3 millisecond window is not included in the correction. So sound travels roughly about a foot per millisecond, so any reflections at 3.5 feet or greater at 600 hertz is not included in the correction filter. As mentioned, as the frequency goes up, the time window gets progressively smaller. As JJ says, at high frequencies, we're only concerned with the direct signal and the early reflections. This is almost the speaker plus speaker stand correction. I hope this comes across clearly because this is one of the key aspects that in psychoacoustic filtering is what differentiates virtually all digital room correction products from the state of the art. The one thing we also need to keep in mind is transient response and pitch recognition. So what we're trying to say here is that, in less than 1 millisecond, the location, our ability to determine location is very acute and happens very fast. Around less than 30 milliseconds, we can sort of assess the size of the signal, how large or how big the signal is. And a little bit greater than 10 milliseconds, we start to recognize the pitch of the sound that's happening. So in the previous slide, we were talking about window widths of 3.5 milliseconds. Clearly, we're just looking at the direct sound. So let's design a FIR filter using these concepts. I'm going to walk through a couple of FIR filter designers to create some high-resolution transfer function and implement them as linear phase FIR filters. We're going to install the filters. We're going to do some comparison listening, because I think it's really important that people understand that there's a particular way that we need to actually compare filter A versus filter B, and that'll become clear once we get to that part. Once we've got through the listening section, we're going to look at the filter design verification. We're going to measure the acoustic response with the filter in the system to verify that the transfer function works as intended, as designed. Okay, let's start with our first real example. And here we're seeing the measured impulse response of both left and right channels as measured at the listening position. And in the bottom chart, we're looking at the impulse response. In the top chart, we're looking at the frequency response derived from that impulse response. And we can also look at the step response. So here I'm looking at the step response. And It is a little bit a ways from our ideal minimum phase response. We can see a couple things going on here. One is that we're seeing some low frequency interaction in the room, very low frequency asymmetry in the room, and we're seeing some other asymmetry as well. We're going to go through this in detail a little bit later, but first we're just going to focus in on the amplitude response, in this case the magnitude of preparing the response for some filtering. As we talked in our slideshow, we're going to apply a psychoacoustic filter. The high frequency treatment is just simply that beyond 23 kilohertz. If there's any brick wall filtering issues, we're going to take care of that. And we're going to extract the minimum phase response and apply a frequency dependent window. And again, based on our example of 15 cycles at the low frequencies and 15 cycles at the high frequencies. So all of those functions strung together are basically a macro, and we're just going to run the macro and apply those functions to both left and right channels. Okay, so with the macro complete, we can see that this is a frequency response that has had a psychoacoustic filter applied to it, extracted the minimum phase response with a frequency dependent window applied as well. And this is what we get. We still have some issues, or we have issues in the low frequencies from 40 to 60 hertz. We've got a pretty big dip there, and then at 70 hertz we've got a pretty big peak. Let's go ahead and go through the next step of what we would normally do, which is we would come up with a target curve. And in this case, I've already got a target curve that I've preloaded, and we can see that there's quite a bit of difference between the target and the peak. How do we actually deal with this peak-to-peak variability? And this happens in virtually every room. There will be at least 20 dB of peak-to-peak variability. So I'm going to show you a nifty little trick here that we can apply what's called a pre-filter that would help us take care of that. So how is that done? Well, in the previous step, I just kind of saved that target curve because I want to show you where the target curve is relative to the frequency response. But what we have to do is load up the measured impulse responses again, which I'm doing the left and right channel here. And then what we're going to do is we're going to take the target and minus the impulse responses, or the frequency response here, and we're going to get basically an inverted response. So how do we do that? We take a frequency domain function and we're going to take the magnitude difference. And so that's the target minus the impulse response, in this case on the left channel, and we're going to put the result into curve 4 and calculate that magnitude difference. We're going to do the same thing for the right channel. We're going to calculate the magnitude difference with the target minus the right hand pulse and put that into curve 5. Calculate the magnitude difference. All right, so if I take away the left and right measured impulse responses, I think you can see what's going on here. But what we want to do is eliminate anything above 0 dB. So how do we do that? Well, you can also apply a magnitude limiter so that we put in 0 dB, and we can get rid of all of those, any signal above 0 dB. So we can do that for both channels. So the magnitude limiter, 0 dB. All right, so you can see what we've got here. Now, if we're wanting to apply a pre-filter, typically, of course, we only want to apply it at low frequencies. So how do we get rid of all of this beyond a certain frequency? So I think, choosing around 200 hertz, I've put a right click, a right marker around 200 hertz. And so the idea is that we just want the left-hand portion from 200 hertz on below and not the right-hand portion. So we can take a time domain function, phase extraction, and the right-hand marker is roughly about 202 hertz. So what we're going to do is extract the minimum phase response, and we're going to overwrite the pulse response that's in curve 1. So we can calculate the phase. So everything above 202 hertz is going to be a straight line. So if we calculate that, we can already see the result. Now that we've done the left-hand pulse, let's look at the right channel pulse. So we're going to do the same thing. We're going to do a phase extraction, minimum phase response into curve 2, calculate the phase. And now I'm going to remove the amplitude differences that we calculated, and this is what we're left with. So these are our pre-filters right here. So what I do is that I save the left and right hand channels. Here, pre-filter left, save, and then pre-filter right, save, pre-filter right, save. What we're going to do is apply these pre-filters when we do the magnitude preparation. So let's go back and load in again curve number 1. We want to put in the left hand impulse response. Curve number 2, we want to put in the right hand impulse response. And now we want to look at our pre-filter definition. Those are the impulse, the pre-filters that I saved, the left and right channel. We want to make that active. And so now when we go ahead and we prepare our magnitude again, we'll see that the pre-filter is going to be applied to this magnitude response. So again, our psychoacoustic filtering, high frequency treatment, extract the minimum phase response, and frequency dependent window of 15 cycles and 15 cycles. And now we're going to see that hopefully below 200 hertz, we're going to see a nice, more or less flat response. And yes, so there we have it. Our peak to peak, our pre-filter has done its job. It's smoothed out the low frequencies quite well. And now we're just left with smoothing out the rest of the response. Again, we go back and we look at our target curve design. I think in this case we want to get a little bit more. I mean, you can play around with this, and here I'm just lifting up and moving the target curve. And again, as we remember, everything above the target curve is what gets corrected. We're going to correct a little bit more of that dip that's still there, but we don't need to correct all of it because we don't really hear that. So I'm going to save that target again. And now the next step is to invert. So this is what we've talked about before, where we're going to invert the response so that we get a nice flat response relative to the target that we're using. Here there's the left and right markers. I've already set that. It's basically out here we don't want to boost any of the natural roll off of the tweeter, and so now I'm just going to run the macro. And here we're getting roughly about 9 dB of filter insertion loss. That's not too bad. We try and keep it between -5 and -10, so we're kind of in the range and we can just leave it as is. Here again we're inverting the prepared amplitude response, prepared magnitude response, where we've not only applied our filtering, but we've also applied some pre-filtering as well. So the next step would be to run the filter generation. And here we can specify our excess phase window, our excess phase correction that we want to apply, our frequency dependent windowing. There's some other features here that I'm not going to get into for this particular demo, but there's many more features that Accurate has that we can get into in another presentation. There's some pre-ringing compensation if we need it. In our case, we don't need it, and we're good as is. So here I'm just going to run the macro, and this is going to generate our filters for us. Again, we're applying some frequency-dependent windowing. In this case, it's going to be the excess phase response. So here we go. We've got our current filter gain is minus 9 dB, so it's not too bad. One of the nifty features that we have available to us is that we can run what's called a test convolution. And what this does is basically give us an idea of what is the end result here. We can actually see that it's looking pretty good. This is the unfiltered frequency response, or projected simulated frequency response that we're going to see. And if we actually applied some smoothing, like we would do in RUW with the 1/6 octave smoothing, for example, we will see that basically the little dips are going to go away. We won't see that in the smooth response, along with, of course, the comb filtering. That will all be gone. If we look down here, we can see in the step response, it's actually looking really good. And I just want to zoom in on it just a little bit here so people can see. We get the no pre-ringing whatsoever. We get almost the ideal minimum phase response that is our speaker. But there is still a few issues that we can see. There's some group delay issues that are making the response asymmetric. This is something that we can actually fix. So let's have a look at doing that. All right, we have Room Macro 6 launched, and we see that we have some group delay, just over 100 hertz or so in the left channel, and another peak at 220 hertz. And we've got some group delay in the right channel at about 146 hertz. So as mentioned, the group delay that's frequency dependent is causing the asymmetry, which will also cause the image to be offset at those frequencies. How do we work with this? We can zoom in on one of these peaks that we're going to do right now, and that is on the left-hand channel. We're going to zoom in, and then we're going to mark the actual peak with a marker here, and then we're going to get the marked frequency, and then we're going to look at what the values are. And here we can see that the frequency is about 223 hertz, and its Q value is 41.6. That looks actually a pretty good match. So we're going to simulate and optimize, and we're going to save the result. So we've got one of them done. So we're going to go back, and we're going to look at the right-hand channel peak, and we're going to zoom in, and we're going to mark it for the right channel. We're going to get the peak, and we're going to get the marked frequency. Yes. And we see we got a pretty good match there. We're going to simulate and optimize. Looks good. We're going to save that result. And then we're going to zoom out again. And we're going to look at the left frequency again, but at around 100 hertz or so. And then here we can raise the Q up a little bit more and have a look. That's a pretty good match right there. So we're going to simulate and optimize. We're going to save the result, and there we have it. And so now what we're going to do is go back to Room Macro 4, and we're going to see that not only have we our pre-filters in there, but now we've got our asymmetry filter that we're going to run Room Macro 4 with. In the result here, we're going to look at the test convolution, and what we should see is tighter values. Yes, that's looking really good. Here we've got our much tighter values in the left and right channel. The symmetry's got quite a bit better. We've got just a little bit left. We could tweak it a little bit more, but generally speaking, that's going to sound really good. All right, here's our second demo of using a DSP DRC fur filter designer, and this one is audio lens, and we're going to do something a little bit different than the previous demo. And if you recall the M2 loudspeakers, JBL M2 loudspeakers that were in the presentation, we're going to take those JBL M2 loudspeakers and use digital linear phase crossovers, and we're also going to add 4 subs. So we really have a 4-way system here. In the case of the JBLs, they cross over from the 15-inch driver, mid-range driver, to mid-bass driver, I should say, to the JBL compression driver and M2 waveguide at 800 hertz. And we've got the JBL 15-inch driver being crossed over at 80 hertz, and we've got another crossover point at 40 hertz. And I'll explain why we've done it this way in a few moments. To look at the actual crossover design, we'll look at the speaker setup here, and we'll look over at the crossover configuration. Here we've got 8 channels that's required, so that's 2 JBL woofers per side, 2 JBL waveguides per side, and 4 subs. And so we're using a Mo2 8-channel DAC in order to facilitate this. And as I indicated before, we've got crossover points, low pass at 40 hertz, a band pass for one of the subs, or 2 of the subs actually, from 40 to 80 hertz, and then from 80 to 800 hertz is the JBL M2 15-inch driver, and then above 800 hertz is the waveguide, and we've done that for both channels. All right, so now that we've got the crossovers, we can perform a measurement, and I'm just going to open up the measurement window here because I want to point something out with respect to a new measurement. Here we're looking at each one of the drivers and the delays per driver, and what I mean by that is that if we're using one of the drivers as reference, if you will, then it's the number of milliseconds difference between that driver and the next driver arriving at the microphone. And so we can see that some of the subs, we call them bass in this particular setup, have about 7.56 milliseconds of delay, and the other sub has 7.71 milliseconds of delay. And the reason for this is that we've got 2 subs at the front of the room and 2 subs at the back of the room near the microphone. And so I just wanted to point this up, that we're measuring the time delay for each individual driver arriving at the microphone. Here we've got the unfiltered measurement of a single speaker. I haven't put on both speakers yet or both stereo system, if you will, or all 8 drivers, I should say. And the reason for this is that this is the full resolution, unsmoothed response or unfiltered response. And we're just going to look at one channel for now, just so I can point out a couple of things. Typically what's done is that we use the correction procedure designer, and here we're going to look at the JBL M2 with the 4 subs. And as we kind of talked a little bit about before, we've got our frequency dependent windowing here for the magnitude, and frequency dependent windowing for our excess phase correction. And we've got some values that I've already put in here, and we could actually work out the FDW math as we've seen that in the slideshow presentation. We've also got true time domain correction or excess phase correction per driver, and then true time domain correction overall as well. Here's what's going to happen. First, we extract the psychoacoustic frequency responses, and we'll show those. They'll show up as smooth responses. Then we correct each psychoacoustic response towards the desired frequency response defined by the crossover and the driver. So the driver is treated like a minimum phase system, so we're extracting the minimum phase here. Then we time align all individually corrected drivers, add up the individual simulator's responses after per driver correction, and we get one global simulation for the speaker. And so now we've got a pretty good, decent sounding speaker, but there's room for improvement in how the drivers collaborate. The process was done on a per driver basis, is now repeated on a per speaker basis. So AudioLens simulates the response for the whole speaker based on per driver correction. We analyze the psychoacoustic frequency response of this and perform a global frequency correction and a global time domain correction. This gives a global correction that is used to adjust the corrections of each driver that was first created in the first step. So the only thing that's left is to generate the simulation, and we'll show that in a minute. So that's a lot to take in. As I mentioned before, we're not going to go through the very deep details of each one of these software packages, just enough so that you can get an idea of what's going on, and in particular, the principles that we talked about earlier about psychoacoustic filtering and frequency-dependent windowing. I'm going to apply this. I'm going to filter the measurement, select our correction procedure, and now we're going through the steps as I mentioned earlier with respect to psychoacoustic filtering and the frequency-dependent windows, both for the minimum phase portion and the excess phase portion. And here again we're looking at just one channel, and I'm just going to walk through a couple things because this will probably help explain why we've got a band pass in between 40 and 80 hertz. So if we just look at the here we go. So this is the sub. This particular sub is one of the front subs at the room. It goes down to about 15 hertz, and we see a little dropout in the crossover region. That's all right. And so if I put in the other sub, and take out this sub, the one thing that you'll notice is that this stub, while it has a lot of output, it's pretty much limited to about 40 hertz, and then it starts rolling off. And so this sub is going to be in the band pass. And, just to speak about this a little bit more, when we go ahead and start convolving these minimum phase responses with the crossover, what's going to happen is that just simply if the response of this sub that we're seeing here is now going to be encapsulated in the linear phase crossover. And the reason why we're using linear phase crossovers is because they sum together perfectly in both the frequency and the time domain. And there's very few crossovers, especially passive crossovers, that really don't do that. Here we're kind of augmenting this hole, if you will, between 40 and 80 hertz with one of the rear subs. So when we add the front and rear sub, we're seeing that we've got a very nice response from 15 hertz all the way up through past the crossover point where we're getting into the 15-inch driver of the JBL M2. And if we look at that, we can see that the JBL M2, if we take off the two subs, left and front sub and left rear sub, which I'm going to do here. Here we can see the JBL M2 woofer, and if you remember in the presentation that there is some filtering that's applied to the woofer down low. Those filters aren't in this measurement. We're bypassing those completely, and we're using AudioLens to provide not only that filtering, but as we will see just shortly, also some constant directivity waveguide EQ, which we'll need. But you'll see that the M2 woofer will fit nicely into the band pass from 80 hertz to 800 hertz, and so it's within its operational range, so when we convolve it into the crossover, it'll be perfect. And if we look at the high frequency response, we can see that the JBL M2 waveguide fits nicely using an 800 hertz crossover point, and with this particular slope that we can adjust. By the way, I didn't show that previously, but that would be another presentation. Remember, we see the drop off quite quickly from about 3.5-4 kilohertz, and that is because as we spoke earlier, the JBL M2 waveguide needs constant directivity EQ, and so we're going to let Audio Lens do that as well. So if I put them all together, we can see that we've got basically from 15 hertz to 24 kilohertz covered. The other thing that I want to show is just jump to the impulse response, because one of the things that we want to look at is the step response of the speaker. So we can go analysis, measurement, step response measurement, and it's quite a lot to see here. And what I'm going to do is zoom in a bit more so that we can just kind of look at what's going on here from a step response perspective. And I'm going to take away one of the sides, stereo sides here. So we're just looking at, for example, here we're looking at the left-hand channel. And I'm just going to, again, take some of this out so that folks can see what's going on. That's the tweeter response that we're seeing. That's what we would expect from the M2 tweeter. And then if we add in the upper mid-range, which is the 15-inch driver, we can see its step response here, fairly close to the step response of the tweeter as far as time offset's concerned. If we look at the bass, we can see a couple things here. One is that there's definitely a delay for the bass to arrive, and we're seeing almost the same amplitude as the direct sound from the bass, so we're starting to see just a little bit of non-minimum phase behavior. And if I actually click in the right bass, the low frequency from the right bass, which is the right front, we can see definitely here that we've got a real non-minimum phase null going on here, roughly about 29 milliseconds after the direct sound. So this is a great way to kind of check to see that the measurements kind of make sense. You want the left and right channels as lined up as best as possible. Audio Lens is going to timeline that when we get into that portion in detail. So if I go back to the frequency response of the one channel, and the next step is, of course, once we've got our smooth responses, and again, just to help facilitate the conversation at low frequencies, it's the room and the loudspeaker that is getting into the measurement. And as we move up in frequency through the diffusion zone around 600 hertz, now we're looking at the direct sound of the M2 waveguide. So the next step is to look at the target curve. So if I hit new target, and here we can view the measurement and see it on the screen. We can zoom in a bit on the measurement, and we can start building a target by drawing these points onto the chart. And we can go ahead and kind of build a target. And what I've done is I've already pre-built a target, so I'm going to open that, add the measurement, and you can see that I've basically gone from 20 hertz to 20 kilohertz is our tilted response, and then I've followed the low frequency roll off of the subwoofer, and I've just left it open at the top. And we can kind of view the smooth response, the smooth target, so that we can have a look at what the target is. If I load the target, the one that we just looked at here, we can see it showing up in the main chart. Now we're ready to invert the response. So when we generate the correction filter, we're going to do the inversion and all of the steps that I mentioned previously in order to create the corrected response along with the simulation. And so we're going to see a simulated result here. So I'm just going to click a few things out. First of all, that is the corrected response and simulated response. This doesn't tell us that there's 14 or more dB of filter insertion loss. That's not how it works. Basically, what we want to look at is the correction filter, which we will in a moment. But I just wanted to point out here that while we still have some narrow dips, those are so narrow in response we don't hear those. And then we've got a little bit of dipping up here at the end of the waveguide towards the end of its response. So it's actually not a bad looking response at all. And if we went over to the step response and we went analysis, simulation, step response plus target, we can see that it literally is virtually textbook perfect. And so we've got the ideal minimum phase response arriving at our ears. So if we pop back to the frequency response again, I just wanted to show you the correction filter that's being applied. And of course, it's being applied on a per speaker basis. And if I take it out, we can see that even though we've got some ups and downs in the correction, really the filter insertion loss for this filter is mostly due for the constant directivity EQ that needs to be applied to the M2 waveguide. So no big deal. We can make up for any kind of filter insertion loss because we're using digital filtering. We're still in the digital domain. And I will show you that when we get to the listening section. So if we look at the filtered measurement versus the simulated measurement, we can see we're getting a really good response. So now that we've got some filters, why don't we give those a listen? So I'm going to share with you the procedures that I go through when I'm comparing filters. And in this case, we're not going to be able to really evaluate the filters because this is not your system, this is not your speakers or room, and you may even be listening to this over headphones. But I think it's important to share the process because there's some things to take into consideration. What I'm showing here is a product called Hang Loose Convolver, which I developed, and it's designed for this very purpose to evaluate high-resolution fur filters that may also have some excess phase correction applied to the filter, which means there's a time delay. So the very first thing to understand is that in this particular convolver, it's what's called a zero latency or a 0 millisecond convolver. That means when we switch filters, we're going to be able to switch them in real time with no delay between the filters. And it's really critical to understand this point because according to the science, we have what's called echoic memory. That's our short-term auditory memory that allows us to remember the sound, record and remember the sound in our head, and it typically lasts anywhere from 3 to 10 seconds. That's a fairly short period of time before our ears start getting used to the sound and makes it hard to remember what was the original sound that I heard versus this new sound that's coming through the system. So that's one aspect that I wanted to bring up. The other aspect is that in each filter bank, in this case we've got the convolver has 6 filter banks. In each filter bank we also have a gain slider or gain control. Remember when we created those filters the first time that they have some filter insertion loss? So what the convolver does is has an auto gain feature that applies the DC gain of the filter and the makeup gain necessary in order to make the same level as if the filter was bypassed. So when we click the bypass button in a filter bank, the level is going to be exactly the same. And that's really critical to understand, as we talked about before, earlier in the theory, where even a 1 dB difference in the level between one filter and the other will give the preference to the filter that is 1 dB louder. And so level matching is quite critical. And so in this case, there's some automation in order to level match the filters, so we don't have to worry about that. The other thing with the auditory memory that we're talking about is that in other convolvers, they're not zero latency or 0 millisecond convolvers. When you go to switch the filter, you'll hear a roughly about 3/4 of a second of blank sound on the switch. That really messes up with your perception of listening to the filter, because it's that transition, the real-time transition between one filter and another, that gives your auditory memory a clue as to the change in tone. So again, that's really important. What we're going to do here is I'm just going to demonstrate the ability to switch these filters in real time. And I've made up these dummy filters, and I've made them up because, of course, we're not listening to your stereo system in your room. But I have made tonal changes to the filters that you'll be able to hear when I switch them, and they're level matched. So let's go ahead, and I'm going to mute the microphone, and we'll give these filters a listen and see if you can hear the differences. All right, we're on the home stretch. Next up are a few examples of validating the FIR filter designer simulations with acoustic measurements. Remember the JBL M2 with 4 subs? I've exported the audio lens simulation into RAW and taken measurements of both the left and right speakers with subs. As one can see, they are pretty much identical. If I was really being picky, I see 2 places for optimization. One is to use a partial excess phase correction to let the M2 compression driver and phase plug do its thing, and the other is to lower the low frequency-dependent window right down to 5 Hz. Whether either is audible is worthy of an A/B analysis using hang-loose convolver. One can see the predicted or estimated step response is virtually identical to the measured response. And it is not just for one mic position, as we will see later. Note the late non-minimum phase peak at 30 milliseconds is now gone, resulting in more bass clarity. Here we can see the results of a room correction transfer function with the right amount of psychoacoustic filtering and frequency-dependent windowing. Just standing a mic up at the listening position and using REW's default window time of 500 milliseconds is letting in all of the frequencies from 20 Hz to 20 kHz with the same window length. In this case, we're just looking at the right channel. I have two views of the same measurement overlaid. The one with all of the up and down spikes or reflections is a full resolution measurement with no smoothing. This does not represent what our ears hear. The straight line with the tilt has a 1/6 octave smoothing applied in REW. This better represents what we hear, which is the envelope, and we can see how smooth the response is with very little variance across the frequency range. If the transfer function was not working as designed, we would see a different frequency response past the diffusion zone, with either too much or too little mid-range or high-frequency energy. Here the response adheres to the design target perfectly with very little frequency response variation. Note that one can apply less correction and get more variance in the response. It is interesting and educational to listen to the same transfer function with varying levels of correction applied. Most folks opt for the smoother sound as it's clearly audible in an A/B test using hang-loose convolver. I normally don't post phase charts, but this illustrates that the time domain correction is doing its job. At low frequencies, any non-minimum phase regions in the response are trending towards the ideal minimum phase response. Not only do we get the smooth bass response, but also it is crystal clear with no room reflections affecting the response. Going through the diffusion zone, more reflections are being let in with less correction. By the time we get to 1 kHz, it is only the direct sound that is getting the frequency correction. When it comes to DSP DRC, we need to be thinking about wavelength and not direction. This validates the FIR filter design using psychoacoustic filtering and frequency-dependent windowing. These are absolutely key aspects for any state-of-the-art digital room correction system. This is the same speaker as the previous slide, but now we're looking at the step response. Here you can see all drivers are time aligned and the subs polarity has been flipped, and the non-minimum phase late low frequency reflection is now gone. We are left with the ideal minimum phase response as drawn by the minimum phase target response. I think it's important to reiterate that it's possible to hear differences between transfer functions, one being time domain corrected and the other not, for example. Hang-loose convolver makes it easy to A/B and even ABX test the differences, as the filters are level matched and switching between the filters is instantaneous. There is limited research here, as I doubt any of the preceding tests were done using high-resolution FIR filters. And other than hang-loose convolver, there is no easy way to conduct a valid A/B or ABX test using FIR filters with excess phase correction. Anecdotally, I can hear the difference, as can other people that have tried this. It's not as audible as the frequency correction, but to my ears, the bass has more clarity and the depth of the field of the stereo image opens up. One of the main characteristics of speakers disappearing is that the frequency response and timing response between channels is near identical, so there is no interchannel frequency or timing response imbalances. Looking at the measured timing response at the bottom left, the sound arrival of left and right channels after the direct sound is not balanced. This disturbs the depth of field and imaging. Note that this room obviously has an asymmetrical setup. Same goes for the frequency response. The key to getting an excellent stereo phantom center image is to ensure that the frequency response of the left and right channel are near identical as possible. Otherwise, you get what is called phantom center image drift, that is frequency dependent. So at that range of frequency or range of frequencies, the image shifts towards one side and can go from side to side as frequency increases, for example. This is especially bad for center image vocals or lead instruments, or even bass guitar can sound off-center. A proper DSP system where both the frequency response and the timing response over time are identical results in a much sharper image that does not drift over frequency or time. The bass is rock solid in the center, and all bass notes sound even and in balance with the rest of the mix. As the saying goes, the bass sits right in the pocket. Here we are looking at the left channel of both the before and after DSP correction for a desktop speaker. In the frequency response, one can see the mid-bass coloration that is always caused by the desktop placement of speakers. I just wanted to show that DSP is highly accurate and precise about smoothing out the response. The corrected response is the red trace. Also note, at 7 kHz and beyond, I've tilted down the response a little bit because it's too bright for me. This is a direct sound adjustment. In the step response, we can see a major reduction of desktop near-field reflections and tuned to the ideal minimum phase response. Note the reflections. They are as large as the direct sound, so not only was there tonal coloration, the image is blurred. Here's an example of a 3-way digital crossover horn-loaded system before and after DSP. I just wanted to point out again, it doesn't really matter what type of speakers are being used in the room that they're being in. Generally speaking, we're going to be able to get the ideal minimum phase response. In this system being a 3-way horn-loaded system, we see a little bit more variance in the frequency response before, but after we can see it's been smoothed right out. Same for the timing response. Again, we're getting that ideal minimum phase timing response. Another example is the Apogee Scintilla, which is a panel speaker before and after DSP. It's a very tough room with the axial modes. As we can see here, the reflections are as large as the direct sound, mostly due to the 30 Hertz peak that we're dealing with here. Once that's reduced, we can certainly smooth out the response, and we can tilt the response up or down as necessary based upon how directive the speaker is and also how lively the room is. We're getting almost the ideal minimum phase response, but we still have a little bit of work that we could probably do here to clean it up. This is the power of state-of-the-art DSP. Based on a single left and right analysis measurement at the listening position, a correction was designed and packaged as a FIR filter and hosted in J-River's Convolver. Through loopback, I'm able to take an REW measurement, 14 in this case, across a 6-foot by 2-foot grid area, which is basically where my couch is. So no matter where I sit on the couch, I get a smooth frequency response. Given that this is a 3-way linear phase digital crossover system with each of the drivers time aligned, we can see in the step response that I get perfect minimum phase response across the listening area with some mid-range and high frequency reflections coming off the back wall at various levels of intensity depending on the mic location and the specular reflections angle of incidence. This is perfectly normal and what we want. As you may notice, all of them follow the minimum phase response. If you have the right DSP model and FIR Filter Designer software, we absolutely can restore the sound quality to our ears with virtually the ideal minimum phase response. Whatever music is on the disc is arriving at our ears with no frequency or time domain distortion added by the loudspeaker or room. Psychoacoustic filtering and frequency-dependent windowing are absolutely key features in state-of-the-art digital room correction. Psychoacoustic filtering avoids overcorrection by not filling in all of the dips in the frequency response, in addition to following the upper envelope at mid-range and high frequencies. Frequency-dependent windowing lets in the direct sound and the low frequencies in the room. As the frequencies move past Schroeder, the time window is becoming less, so by the time we are through the diffusion zone, we are only correcting the direct sound of the speakers, or speakers and stands, as JJ would say. The walkthrough and examples I have shown illustrate that we can achieve the ideal minimum phase response with virtually any loudspeaker in any room. In fact, having DSP'd over 100 125 different loudspeakers in rooms from around the world over the past 18 months has illustrated that the DSP modeling approach and solutions are robust and repeatable. The good news is that state-of-the-art DSP can be purchased for under $450. While many folks are using USB measurement microphones for ease of use, there is an issue where the analog to digital converter that's running in the microphone is a different clock than what is running the DAC. So timing issues may present themselves as clock drift, or a start time for one channel may be different for the other channel. Most DSP software can accommodate this to one degree or another, but it's best to avoid the issue completely by getting a good analog mic. Earthworks makes high-quality analog measurement microphones, and it will require a separate mic preamp, or most of the Pro Audio A to D, D to A converters also has mic pre's built in. Almost all hardware-based DSP products have limited capabilities. If truly fur filtering at low frequencies, hardware DSP typically has enough resolution for the equivalent of 2 EQ sliders below 100 Hz. This is the exact area where we need a lot more frequency resolution in the modal region. Conversely, software with fur filters has a graphic slider at every 0.7 Hz, so more than 100 sliders below 100 Hz. Or the other issue is that IIR filters are being used below the transition frequency, which does nothing to correct the non-minimum phase behavior that's in the room. IR filters can smooth the frequency response, but no time domain correction. So only half the transfer function is being corrected. Remember, we're talking about state-of-the-art here. Multiple subs generally are a good thing. However, it does not automatically guarantee a smooth response. Even if you have 4 subs set up perfectly, you'll still get around 20 dB of peak-to-peak variation in the low-frequency response due to room resonances. There's just no way around it. So DSP is still required. But if the subs are complementary, a very smooth response can be achieved. I can't underline this enough. Not all DRC DSP products are the same. Factoring out almost all hardware products that don't have enough DSP power, we are left with quite a few software products. Many rely on good marketing, but the reality is that very few can actually design and generate a proper transfer function. I have reviewed over a dozen software products, and so far only these 4 make the cut in being able to meet the modeling requirements and design a proper transfer function. If there are popular names missing, it is because for one reason or another, or many, that the DRC software cannot create a proper transfer function to restore the ideal minimum phase response. I should note I have not reviewed all software, all DSP DRC software, so there is a possibility that there are more out there, and I would be looking for its psychoacoustic filtering and frequency-dependent windowing capabilities as the minimum entry level. If the DRC DSP can't do that, then it's not a contender for state-of-the-art room correction. I've written a couple of review articles on Yuli's Accurate Berndt audio lens and a review of David's Focus Fidelity Designer. I wrote a book on accurate sound reproduction using DSP that uses Accurate as the DSP software for the hands-on portion of the book. With respect to open source DRC, a couple of folks on DIY Audio have great examples of using this software. Also, the documentation is a good read on psychoacoustic filtering and frequency-dependent windowing. Another comment about single versus multiple measurements. All of the software listed can take multiple measurements. But with Accurate and Audio Lens, I find that a single measurement not only produces a more accurate correction at the listening area, it also extends across a 3-seat sweet spot, as shown in one of my previous slides, and I go into great detail in my DSP book. David's Focus Fidelity Designer is the only DSP fur designer that gets multiple measurements correct. Focus Fidelity uses multiple measurements to build a transfer function, and from there apply less correction to features which changes with position. Focus fidelity avoids the overcorrection problem by not just averaging the multiple measurements like so many other DRC packages do. On the topic of watching movies using transfer functions with time delays, most video files I know will rip the Blu-ray or DVDs to MKV format and then use JRiver to watch the movie, as the video engine is aware of the FIR filter latency and will compensate so lip sync is perfect. If you're streaming video, then as a last resort, one can apply a frequency correction only and forego the excess phase correction. While the bass may not be quite as clear, it will be even in response. As you may remember, we still have access to 32,768 graphic sliders that other DSP/DRC software do not have. I hope you enjoyed understanding the state-of-the-art of digital room correction. Of course, there's much more to cover, as I just briefly dipped into the FIR filter designers. If there are more topics using state-of-the-art DSP that you would like me to cover, drop me a line at mitch@accuratesound.ca, and I'm also on quite a few audio forums as Mitchco or MitchBA on the DIY audio forum. If interested, you can find out more about me via Jason's YouTube interview or Chris's podcast, or if you want to get right to the technical bits, you can find my book on accurate sound reproduction using DSP on Amazon. Happy listening.